All right, welcome to another deep dive. You ready to get into it again?
Absolutely. Always excited to dive into these fascinating topics.
Okay, cool. So today we are tackling Russell's paradox, which, if you've never heard of it before, is going to it's going to really bend your brain a little bit, make you think about things maybe you hadn't thought about before.
Yeah, it's one of those ideas that seems simple on the surface, but has some really deep implications.
Absolutely, and we're going to be looking at we have an excerpt here from the Stanford Encyclopedia of Philosophy on Russell's paradox to guide us.
Great source. Definitely a good starting point for this.
Yeah, so let's jump right in. Now, the story kind of begins with this idea in early set theory called the naive comprehension principle.
Right. The idea that for any, describable collection of things, you can have a set, like a set of all the books in a library or a set of all the even numbers.
So it seems pretty straightforward, right? Like, yeah, if you can describe it, you can group it together into a set.
Exactly. But that's where Russell's paradox comes in and throws a wrench in the works.
Oh, I am so ready for this range. So walk me through it. How does this seemingly innocent idea about sets lead to a paradox?
Okay, so imagine trying to create a set of all sets that don't contain themselves. We'll call it R. Now, here's the mind-bending question. Does R belong to itself?
Okay, I'm already feeling my brain starting to twist a little bit. So this set R is basically like a container for sets that are kind of loners. They don't include themselves, right?
Precisely.
But then if R does contain itself, it would have to be one of those loner sets, which means it shouldn't contain itself. But if it doesn't contain itself, then it fits the description and should be in the set.
Yeah, it's a classic catch-22 situation. No matter which answer you choose, you run into a contradiction.
It's like a logical loop with no escape. I mean, it seems so simple, just this one question, but it completely unravels this fundamental idea of sets.
Right. It shows that the naive comprehension principle, as intuitive as it seems, isn't quite as straightforward as we might think.
Yeah, definitely not. This is way more than just some abstract thought experiment. This paradox had real consequences for the world of mathematics.
It was a major shakeup, especially for logicians like Gottlob Frege, who was working on this huge project to try and build all of mathematics on the foundation of logic.
I can only imagine, like you're working on this massive project, you think you're close to the finish line, and then boom, this paradox comes along and just throws everything into question.
It was a huge blow. Imagine receiving a letter outlining this paradox just as your work is about to be published.
Oof, I would definitely not want to be in his shoes at that moment.
Well, that's exactly what happened to Frege. He got a letter from Russell explaining the paradox, and he was understandably devastated. He even ended up adding an appendix to his book, which is Grundgesetze der Arithmetik, at the last minute just to try and address this paradox.
Talk about a major edit. That really shows just how deeply this discovery impacted the mathematical community. So what happened next? How did mathematicians respond to this crisis in the foundations of set theory?
Well, there were a bunch of different approaches. Even before Russell, Cantor, the guy who really pioneered set theory, he had a hunch that not all descriptions could be neatly turned into sets. He was already exploring the idea of putting some kind of limits on set size to avoid these kinds of contradictions.
So he was kind of ahead of the curve, sensing that things could get a little out of hand with this unrestricted set creation.
Definitely. But then Russell himself, his initial attempt to resolve the paradox was through this thing called the theory of types. It's a bit complex, but essentially it creates a kind of hierarchy of sets to prevent those self-referential loops that lead to the paradox.
So like a set of rules to make sure you're not accidentally building a paradoxical set.
Exactly. And then you have other mathematicians like David Hilbert, who thought the answer lay in building a more rigorous axiomatic system for set theory. He really pushed for clear definitions and rules to avoid these kinds of paradoxes popping up in the future.
So kind of like a preventative approach, making sure the building blocks themselves are sound. It sounds like there was a lot of debate and different schools of thought emerging from this one paradox.
Absolutely. There were also mathematicians like Poincaré and Brouwer who were big proponents of this idea called constructivism. They basically argued that you should only accept a mathematical object if you can actually construct it step by step, which implicitly rejects the broad, naive approach to sets that led to the paradox.
So a lot of different perspectives and solutions on the table. It's amazing how one seemingly simple paradox could lead to such a rich exploration of ideas.
Yeah, and one of the really interesting things about Russell's paradox is how it connects to this other big idea in math, Cantor's diagonalization. Might seem like a bit of a detour, but it actually helps us understand the paradox on a deeper level.
Okay, yeah, Cantor's diagonalization, I remember hearing about that. It has something to do with different sizes of infinity, right?
Exactly. It's this really clever method that Cantor came up with to show that, not all infinities are the same. He proved that there are actually more real numbers than natural numbers, even though they're both infinite.
Wait, hold on. More real numbers than natural numbers. How is that even possible? They're both infinite.
I know, it's mind-blowing, right? But Cantor's method shows that even within infinity, you can have different levels of, like, bigness. Imagine you're trying to list out all the real numbers, and then Cantor's method shows you how to construct a new number that's not on your list, no matter how complete you think it is.
Okay, I think I'm starting to see why it's called diagonalization. You're essentially making a new element by going diagonally across this hypothetical list and changing things up. But how does this relate back to Russell's paradox?
Well, think of it this way. Russell's paradox is kind of like using diagonalization, but instead of using it on numbers, he's using it on the idea of sets themselves. It's like he took Cantor's method and turned it inward to expose this flaw in how we define sets with the naive comprehension principle.
So he's using this diagonalization idea to basically show that defining sets based on any description can lead to these crazy contradictions.
Exactly. And seeing that connection between Cantor's diagonalization and Russell's paradox helps us understand it's not just some random quirk of logic, is actually a direct result of the way sets work and how we try to define them.
This is really making me appreciate how all these different mathematical concepts are connected. It's like one big web of ideas. But going back to Russell's paradox, we talked about all these different solutions, like Russell's theory of types and Zermelo-Fraenkel set theory. Where do things stand today? Like, do we have a definitive answer to this paradox?
Well, in modern set theory, we've basically solved the paradox within our systems, like with Zermelo-Fraenkel ZF. The axiom of separation, which puts limits on how you can create sets, prevents us from actually making that set of all sets that don't contain themselves.
So we've kind of built a fence around the paradox, but the questions it raised are still there.
Exactly. Even though we've figured out ways to avoid the paradox in our systems, the philosophical questions are still being debated. It makes us rethink what a set really is, what the limits of logic are, and even the nature of infinity.
So even though we've kind of sidestepped the paradox in practice, it still has this power to make us think about some really fundamental stuff. It's like this seed of doubt that keeps growing and making us question things.
Absolutely. And one of the biggest questions that comes out of all this is about the limits of what can be a set. If a universal set is off limits, where do we draw the line? What are the boundaries of this whole world of sets?
Whoa, that is a really good question. It's like we've mapped out this huge territory of sets, but there are still these unexplored areas, these places we can't go.
And that's part of what makes Russell's paradox so fascinating, right? It's not just about solving a problem, it's about grappling with these big questions about the limits of knowledge and what math really is.
This whole deep dive has been incredible so far. We started with this basic idea about sets, and now we're talking about infinity, diagonalization, and how this one paradox changed the way we think about math over a century ago. I have to say, my head is spinning a little bit.
It's a lot to take in, for sure, but that's what's so great about exploring these foundational ideas. They really push you to think differently and expand your understanding of the world. And while Russell's paradox might have revealed some problems in our systems, it also led to more rigorous and complex ways of thinking about logic, math, and beyond.
So it's not just about the problems, it's also about the solutions and new ideas that came from it.
Exactly, and maybe that's the most important thing to take away from our discussion today. Russell's paradox isn't just some old puzzle. It's a reminder that learning and discovery is a journey, not a destination. And sometimes the most amazing insights come from confronting the paradoxes that make us question everything we thought we knew.
I love that. This has been such a fascinating exploration. Thanks for taking us on this deep dive into Russell's paradox. I have a feeling you're going to be thinking about these ideas for a long time. Yeah, it really is amazing how a paradox that started with sets has connections to so many other areas.
It shows how interconnected everything is. Like in computer science, for example, Russell's paradox has implications for how we design programming languages and how we think about those data structures that refer back to themselves.
Oh yeah, I can see how that would be a problem. Like if you have a program that refers to itself in some contradictory way, things could get really messed up.
For sure. And in philosophy of language, it's been used to explore, the limits of language and how we can even end up contradicting ourselves when we try to describe the world.
So it's not just about sets anymore. It's about the very tools we use to think and talk about things. It's pretty deep.
It really is, and it shows how powerful Russell's paradox is. Even with all the progress we've made in logic and math since it was discovered, it still makes us ask these fundamental questions about the nature of knowledge, the limits of our systems, and even if it's possible to create a completely consistent and comprehensive view of reality.
It's kind of humbling. This seemingly simple idea about sets leading to these huge questions.
Definitely, it really highlights the importance of critical thinking and questioning assumptions, even the ones that seem really basic. Russell's paradox reminds us that knowledge is always evolving and there's always more to discover.
This deep dive has been a real eye-opener. We've gone from the naive comprehension principle to Cantor's diagonalization, looked at different solutions to the paradox, and ended up talking about the limits of set theory and the nature of knowledge itself. I gotta say my head's spinning a bit.
That's the thing about these fundamental questions. They make you think differently and see the world in new ways. And while Russell's paradox pointed out some problems, it also led to better and more sophisticated approaches to logic, math, and other fields.
So it's not just about the problems, it's about the solutions and new paths of inquiry that it sparked.
Right, and that's a key takeaway from our conversation today. Russell's paradox is more than just a historical curiosity or a logic puzzle. It's a reminder that learning is a journey. And sometimes the most profound discoveries come from facing paradoxes that challenge our understanding and make us rethink what we thought we knew.
Well said. That was a truly fascinating exploration. Thank you so much for guiding us through this deep dive into Russell's paradox. I have a feeling this is something I'll be thinking about for a while.
It was my pleasure. And remember, next time you encounter a paradox, don't avoid it. Embrace the challenge and see where it leads. You never know what incredible insights you might find.